Ever wondered how we measure the flow of water through a dam or maybe the electric field passing through a surface? Well, the answer comes from this really powerful idea in multivariable calculus called flux. So let's dive in and break down exactly how it works.
Here's our game plan. We're going to start with what flux actually is, get the intuition down. Then we'll look at the big formula we use to calculate it. After that, we'll work through 3 classic examples, from simple disks to curved domes, to see it in action. And we'll wrap it all up with a clear step-by-step playbook you can use for pretty much any flux problem.
All right, first things first. Before we even think about touching an integral, let's build a really solid gut-level understanding of what we're trying to measure here. At its absolute core, flux just answers a pretty simple question. How much stuff is flowing through some surface? Now, this stuff could be something physical, like water, or maybe something less tangible, like heat or an electric field. We represent all of this stuff with something called a vector field, which is basically just a map that tells us the direction and strength of the flow at every single point in space.
Okay, so for the more formal definition, if you've got a velocity vector field, let's call it F, that represents a fluid, then the flux is the volume of that fluid passing through a surface S in a given amount of time. It's really a rate of flow through an area.
Now, this right here is the absolute key to understanding everything that comes next. We only care about the part of the flow that's perpendicular to the surface. Think about it. Any flow that's parallel is just kind of skimming along the side, right? It's not actually going through it. And the entire Flux integral is designed specifically to isolate and measure just that perpendicular part.
All right, now that we've got the concept down, let's look at the mathematical tool we actually use to calculate this perpendicular flow.
And there it is, the Flux integral. I know it looks a little intimidating with the double integrals and that cross product, but stick with me. We're going to unpack it piece by piece. The coolest thing about this formula is that every single part directly relates back to that physical idea we just talked about.
So let's break it down. First, this f of r of u part, that's just us plugging our surface into the vector field. Simple enough. Now this next piece, the cross product ru cross rv, this is the magic ingredient. This gives us the normal vector, a vector that points straight out, perpendicular to the surface at every single point. Finally, we take the dot product. The dot product is a fantastic tool that tells us how much one vector is pointing in the same direction as another. So when we do f dot the normal vector, it perfectly isolates just the component of the flow that's going straight through the surface. It's brilliant, really. Okay, theory is great, but let's get our hands dirty and see how this formula actually works in practice. We're going to walk through 3 examples, starting with a nice flat surface and working our way up to more complex curved ones. So for our first case, we've got a super simple setup. The vector field is just f equals 0, 0, 3, meaning it's pointing straight up, constantly, everywhere. And our surface is a flat horizontal disk. Now, before you even write down the integral, you can do this awesome little logic check. It's a great way to catch mistakes later. Since our flow is constant and it's hitting the surface perfectly perpendicularly, the total flux should just be the strength of that flow multiplied by the area of the disk. It gives you a great ballpark for what the answer should be. And would you look at that? The field strength is 3. The area of a unit disk is just pi. So our logic check says the answer should be 3 pi. And when you go through the whole integral calculation, that's exactly what you get. The math confirms our intuition. Perfect. Okay. A flat surface was pretty straightforward. But what happens when the surface is curved? Let's level up. We're going to find the flux of a radial field, that's F equals xyz, flowing out from the center of a sphere. You can picture this field like light radiating out from a light bulb in all directions.
So the process is the same, but the steps get a bit more involved. First, we have to parameterize the sphere, basically creating a map for it using spherical coordinates. Then we use that map to calculate the normal vector, which points straight out from the sphere at every point. After that, we do the dot product of our field and that normal vector, which in this case actually simplifies down really nicely to a cubed times sine phi. And finally, we integrate that result over the whole sphere.
And once you run that integral, you get a final flux of 4 pi times a cubed. It's a really clean result for a classic problem.
All right, we've done a flat disk, we've done a perfect sphere. For our final challenge, let's tackle a surface that's a bit more, interesting. We're going to find the flux of the field F equals y, x, z through a paraboloid, which is basically a little dome shape. Okay, the strategy here is everything. We start by parametrizing the surface as a graph. We find our normal vector, we do the dot product, and we get this expression, 4xy plus 1 minus x squared minus y squared. Now, trying to integrate that as is looks like a nightmare. This is where a lot of people get stuck. But here's the pro move. Switch to polar coordinates. This makes the integration so much simpler. And even better, because of the symmetry of the integral in polar, that really annoying 4xy term, it just completely vanishes. It goes to zero. It saves you a ton of work. And after you integrate that much simpler expression, you'll land on the final answer. The total flux is pi over 2. So, after seeing all those different examples, you might be thinking, is there a general strategy I can just always follow? And the answer is yes, absolutely. Let's boil this whole thing down into a simple, practical playbook. Here it is, your 5-step guide to solving any flux problem. 1. Parameterize your surface. You need that map. 2. Calculate the normal vector, which tells you the through direction. 3. Evaluate your vector field on that surface. 4. Compute the dot product. This is where you isolate the perpendicular flow. And finally, 5. Integrate that result to add it all up. If you just follow these 5 steps every single time, you can handle any flux calculation they throw at you.
So what's the big picture here? We started with a really simple idea, flow through a surface. And we've built up this incredibly powerful 5-step method to calculate it for all kinds of complex fields and weird shapes. So the question I want to leave you with is this. Now that you know how to calculate flux, what else could you measure with it? Think about electromagnetism, fluid dynamics, heat transfer. The applications are absolutely everywhere.